9 is L'Hopital's rule. And here in this situation, as Logan likes to say, it is the hospital's rule. And I'm trying to remember, I believe the other spelling, I need to look it up, I should have looked this up, is, that doesn't seem right, where it's Hopital. And there's like a little, is it over the O or the A that there's a little, what's that? I don't know what that mark is called. It's more than just an accent mark. I don't know. Okay, so actually, okay, if you look in your book, it's supposed to be over the O. Sorry. Okay, so realizing, okay, you will see it as what looks like Le Hospitals. It's also L'Hopital's, okay, and you will see it in both. In all honesty, on AP, will they say use L'Hopital's rule here? No. You have to know when to apply it. So I don't know that you would ever have to worry about how it's spelled on the test, but, you know. Okay, so L'Hopital's rule is based on G.F.A.M. de L'Hopital, I don't know, and John Bernoulli made this rule to extend our knowledge of the limit as a quotient. We have a specific time we use L'Hopital's rule, and that is when we hit what is called an indeterminate form. When we take a limit and we get something such as 0 over 0 or infinity over infinity. That's when we can apply L'Hopital's rule. Now, in some of those cases, we've seen some of these cases of 0 over 0, but we then have been able to factor and then to cancel it out. And then we've been able to work it. And that could still work in some of these cases. But the focus of L'Hopital's rule is when you get 0 over 0, and you can't do anything else with it. It won't factor. Okay? We can use L'Hopital's rule. And what L'Hopital's rule says, if the limit as x approaches a of f of x over g of x, so two different functions, is an indeterminate form. And notice, indeterminate forms are 0 over 0, infinity over infinity. So if you get one of those indeterminate forms, then what you can do is you can do the limit of x over a of the derivative of the top over the derivative of the bottom, and then you can try it again. If you still can't take the limit, if you still get an indeterminate form, you can try L'Hopital's again. You can use L'Hopital's repeatedly, however many times you need to, till you get to a point that is no longer in an indeterminate form. Okay? You should never just jump right in and say, okay, I'm going to use L'Hopital's as the limit. You need to have an indeterminate form to start using L'Hopital. Okay? Okay, let's try example 1. Evaluate the limit as x approaches 0 of sine x over x. So if we just do what we know and we try and plug in 0, what is the sine of 0? 0. And when you plug in 0 for x, you get 0. So as this is right now, we would get 0 over 0. Okay? And that's not a value of 0, it's not a value of infinity, it's an indeterminate form. We don't know what it is. So we're going to apply L'Hopital's rule. Now, let's see, how do I want to do this? I'm going to go official notation here at the beginning. We won't always do this, but I'm going to say the limit as x approaches 0. And then we're going to do the derivative of the top, derivative of the bottom. So I'm going to say to take the derivative, or to indicate that I want to take the derivative, I'm going to use that notation of d dx. And that's just saying we're going to take the derivative with respect to x. I'm going to put that in front of the numerator and in front of the denominator. And again, it was because it was in that indeterminate form. So, you also notice, as annoying as it is, I'm rewriting that limit sign every time. So we don't forget that we're taking a limit. What is the derivative of sine x? Cosine x. What is the derivative of x? 1. And so now we're doing the limit as x approaches 0 of cosine x over 1. So what do? Plug in 0 again. Cosine of 0, officially over 1 if you still have that. What is cosine of 0? It's 1. And so what does this limit come out to be? 1. Now, can you graph this to confirm? And my point is that yes, a graph should confirm. If I have sine of x divided by x, and please note, anytime you are dealing with sine and graphing it, be in radian. But you get this kind of wavy thing. Can you guys even see that? It's really dark. I think because I have this turned off, because I have that turned off, because I don't want there to be a reflection. Let's do different. Let's do it that way instead. Okay? But you've got this wavy line, but what's happening? As x approaches 0, what's that graph doing? It's going up to a value of 1. So the limit did exist. There was a limit. It was 1. And L'Hopital's helped us find that without having a calculator by our side, right? So this is the type of rule you would use without a calculator. Questions? Okay, let's try example 2 then. The limit as x approaches 0 of cosine x minus 1 over x squared. What are you doing first? Yeah, you've got to plug in 0 first and see where we're at. So we'd be doing cosine of 0 minus 1 over 0 squared. Well, we just talked about cosine of 0. That is what? 1. And 1 minus 1 is 0 on top. 0 squared is 0. And we have 0 over 0, which is the indeterminate form you find most often, to be honest. Okay? So what are we going to do here? We're going to still going to be the limit as x approaches 0. We're going to do the derivative of the top function, so the derivative of cosine x minus 1, and the derivative of the bottom function, which is x squared. Still, the limit as x approaches 0. What is the derivative of cosine x minus 1? Negative sine x. Derivative of x squared. 2x. Now what? Plug in 0. What's negative sine of 0? 0. What's 2 times 0? 0. What just happened? We got that indeterminate form a second time. What did I say, though? No. We do it again. We're going to do L'Hopital's rule again. Good news is that L'Hopital's rule isn't that difficult. It's not hard to apply, is it? You're doing derivatives. Derivatives are something you've been doing for quite a while in here. So, repeat the process. The limit as x approaches 0. This time we're doing the derivative of negative sine x over the derivative of 2x. Limit as x approaches 0, derivative of negative sine x is negative cosine x. Derivative of 2x is 2. Well, I definitely know I'm not getting 0 over 0 here. What is negative cosine of 0? Negative 1 over 2. So final answer of, off the screen you can't see it, negative 1/2. Okay, questions? Are we okay with L'Hopital's? I like L'Hopital's. There's certain things in calculus that I just like. And I think I like this one just because it's easy to use. And once you get in the habit of it, it's easy to recognize when you need to use it. So, okay, example 3. Limit as x approaches 0, x cubed minus 4x over x squared minus 2x. What are your thoughts? Okay, still 0 over 0, yes? Okay, so we have to come up with a plan B. And so the limit as x approaches 0, we're going to do the derivative of x cubed minus 4x over the derivative of x squared minus 2x. What are those derivatives?
3x squared minus 4 over 2x minus 2.
3x squared minus 4 over 2x minus 2.
Do we have to show that we're taking a derivative, or can we just do it?
I think you have to show. Trying to think AP test here. One thing, and I haven't really talked about today, I focus on it more later, but one thing you have to show on the AP test is you have to show why you need to use L'Hopital's rule, which they always tell us that you need to show that the limit as x approaches 0 of cosine x minus 1 equals 0, and you need to state that the limit as x approaches 0 of x squared equals 0, or in this case, the limit as x approaches 0 of x cubed minus 4x equals 0, and the limit as x approaches 0 of x squared minus 2x equals 0. You have to state those as separate entities. But then to actually write this part that you're taking the derivative, I don't think you'd actually have to do that. You would just be able to jump in and say, okay, it was this, now it's this. But you would have had to say, okay, I'm taking this, I'm using L'Hopital's because this limit was 0 and this limit was 0. Okay? Okay, did you guys finish this one? You put in 0. 0 minus 4 over 0 minus 2, which is 2. Is that the only way we could have done that problem? And I guess if nothing else, the answer is, oh, she's asking that. It must not be. Okay. Well, if you would have gotten 0 over 0 before today, what might you have tried? No, use that for infinities, if it's x approaches infinity. But is there some factoring that could happen? Think about this if we factor real quick. I just want to show you. that if we did this as factoring, limit as x approaches 0, on top there's a GCF of x, which then leaves you with x squared minus 4. And the denominator is a GCF of x, which leaves you with x minus 2. What can you still do on top? Yeah, on top you already have x. X squared minus 4 goes to x minus 2, x plus 2. And the denominator is x, x minus 2. What happens with all those pieces? X minus 2's cancel, x cancels. And this becomes the limit as x approaches 0 of what? X plus 2. Which, put in the number, and 0 plus 2 is 2. Am I saying you had to do it that way? No, not at all. Okay? Some of it depends on what you catch. Either way, you had to do something because this original limit was 0 over 0, wasn't it? So whether you use L'Hopital's or whether you use factoring, my reasoning for showing that is just proving to you, you get the same answer, right? That's my main reasoning for showing it. That it doesn't matter if Nathan sees L'Hopital's and Logan sees factoring. It doesn't matter if they do it opposite ways. They can still meet in the end. Okay? Okay. 2 more examples, I believe. I don't believe I have anything on the back, do I? No. So, limit as x approaches 1 of natural log of x over 2 minus 2x. Thoughts here? We put in 1, the natural log of 1 over 2 minus 2 times 1. Well, in the denominator, 2 minus 2 times 1 is going to be 0. What is the natural log of 1? It's 0. That was a guess, wasn't it? And that's, I will say, that's a good value to know. Okay, that is a good value to know. Can you guys visualize the natural log graph? The natural log graph is this one right here. And what do you know this point is? 1, 0. Because then the exponential graph is this one right here. And what's that point? 0, 1. So this is y equals e to the x. This is y equals natural log of x. And I'll be honest, if I'm counting on myself, when I have to stop and think, crud, what's the natural log of 1? I go to this. Because then, what's the natural log of 0? There is none. Because my graph doesn't touch the y-axis, right? You can't do the natural log of 0. If you're comfortable with those graphs, it's helpful. Okay? And I say this because, are you allowed your calculator in all parts of the test? That's why it's helpful to some, because they would expect you, this is a problem that could be on the non-calculator portion. They want you to know that the natural log of 1 is 0. So, okay. We got 0 over 0. Did you guys start into L'Hopital's? The limit as x approaches 1. And we're going to do the derivative of natural log of x over the derivative of 2 minus 2x. Okay, still the limit as x approaches 1. What's the derivative of natural log of x? 1 over x. What's the derivative of 2 minus 2x? Negative 2. Now, for the benefit of what we're doing here, you can just continue. You don't have to make that better form. 1 over x becomes 1 over 1 over negative 2. This answer becomes negative 1/2. Now, random, while I'm sharing random knowledge day, 1 over x divided by negative 2. If you need to clean that up, what would that clean up to be? Realize that would be this expression right here. It becomes 1 over x over 2 becomes 1 over 2x. That's a good connection to know. Okay, one more example. Limit as x approaches infinity of cosine x plus 2x over 6x squared. Okay, so what are you thinking?
I don't know how to take the cosine of infinity.
Okay, valid point, valid issue. Okay, so can you visualize the graph of cosine with me? What's the graph of cosine do?
It oscillates between 1 and -1.
Okay, and I saw, okay, it lies between -1 and 1. I saw Logan draw this back here. Is it just this? It goes up and down, up and down, up and down between -1 and 1, right? So that cosine x goes up, down, up, down, up, down between -1 and 1. And you're going to add that to 2 times infinity. But what's 2 times infinity? Still infinity, right? So 2 times infinity is still infinity. And if you're adding a value that's -1 to 1, you're still going to be at infinity. Does that make sense? That -1 to 1 value doesn't really matter, at least when we're talking about infinity. And then what about 6 times infinity squared? A bigger infinity, right? Okay, so we have an indeterminate form. This time it's infinity over infinity. L'Hopital's rule still applies the same. The limit as x approaches infinity, and we're going to do the derivative of cosine x plus 2x over the derivative of 6x squared. So still the limit as x approaches infinity. What's the derivative of cosine x plus 2x? Negative sine x plus 2. And what's the derivative of 6x squared? 12x. Okay. Whoops. 12x. I said 12x. You guys said 12. It told me 12x, but I still only wrote 12. Okay. What's your thoughts?
So I'm still on the boost between 1 and -1.
Mask back off anyways. I'm eating hair. Okay. So sine goes between, it's negative sine x, but it's still, depending on where you hit it, it's still up and down, up and down. And so that value goes from -1 to +1, yes? So as we look at this on top, if that value is anywhere between -1 to +1, and then we're going to add just a plain old 2 to that value, what kind of value do I have on top then? Between 1 and 3? Because if you're at the lower end of -1 and you add 2, you're at +1. If you're at the higher end of 1 and you add 2, you're at 3. So my top value is something in the interval from 1 to 3. Now, how we handle that depends on what our denominator does. What about our denominator? 12 times infinity is infinity. Okay. So what does a small value, a small finite value between 1 and 3 divided by infinity? Basically 0. And since this is limits, it's what is it approaching? And when you take that small finite value that is no smaller than 1 and no bigger than 3, that's the important part, no bigger than 3, and you divide it by an infinitely increasing bigger number, you're going to be approaching 0. Okay? Note your little bottom corner down there. 3, 4, and 5 are becoming 12, 13, 14 from 77. And other than that, I hope you liked your L'Hopital's rule. You didn't like it?